if everyone could get towards the stage. We're gonna take a photo of the stage.
So how is Hirsch Rabbits doing?
I really don't know. I don't know.
Close to retirement or something? But you were this group at one point?
No, I wasn't.
You were Princeton.
No, that's Dennis. I'm Alex.
Okay. Your advisor was at Princeton.
Yeah.
Okay.
Yeah.
I was thinking you don't even look like Dennis Bondar anymore. It's like.
I should probably.
You're Alex.
Were you asking about Hirsch Rabbits?
No, I had a couple of papers with you.
I'm guessing we don't want to take a picture of my title page.
Oh no, I think that would be on.
Yeah.
Good advertising.
Yeah.
We could pull up the little logo from CCD that says, "We touch everything," and I'm like, not since Monday, you don't touch anything.
Right, sure thing.
Let's put the quilt in the couch. Just go bring up a browser.
So,
You can bring it up on your computer.
is this the best? Am I blind, or is this is really, really dark and hard to see?
Yeah.
It's a bit dark. It's not the best.
It's not a bit dark.
You had
It's
it, it was
really,
the-
okay, look at that.
Yeah, okay, that's
Okay.
oh, that'll be impossible.
It's dark, and even with my glasses on, the letters are
Why
blurry.
did they change the colors on that? It used to have orange lighting, orange at the top. Hold up.
That's good, that was good.
That is. That.
Yeah, well, just, it's the
But,
quilt.
but even these are kind of dim. Is that the bulb?
No, the projector. It's the fact that we have lights on the stage.
Oh, let's kill the lights on the stage.
Then you can't see the audience.
I don't want to see the audience. I want to see
Okay,
the audience.
that's fine.
Mark.
I'll go down one extra light setting.
Yeah, one flight more. I mean, you could kill that without killing all those.
Yeah, we got
Yeah,
6
let's-
light settings.
We're gonna take the group picture right now.
Okay, that's
You
fine.
want us on the stage or?
Yes. On the stage.
All right, so gather around.
They tried and couldn't find anything.
Oh, should we just, maybe we should just turn off the projector. It's like letters on the wall.
Yes.
We'll be, well,
You're gonna like 40 shots.
no, because the projector hardly hit us in the night.
Uniform.
That's what I was saying. The LSU logo will actually show on the photo.
And that's
Really?
That's cool.
Speaking of Singapore. Paras, get your paras down here into the photo. Go to the front, short. Short guys in the front. Whoop. There you
All right, just let us know.
So you guys could bunch a little bit together. I'm trying to get everyone in front of the screen, so people over
go.
there.
No shaking hands.
Like you're trying to catch the virus.
Yeah. Act like you're trying to catch the
Feeling in front if they want.
Everyone say iPhone transmission.
This is my ring.
In the second row. So you said you too. It's real thin right in the center. If you guys want to move over, there's 3 rows over here.
Put the midgets in front. Dr. Midget.
Congratulations.
Congratulations, Doctor.
Support after that comment.
Well, we had it. Who was the shortest one in the group? Any?
Oh, it's
used to
definitely
be you. Yeah.
All right, ready?
I think Eliza might be shorter.
Corey, what?
Oh, Corey was like
All right, going on 3.
4 feet max.
1, 2, 3. All right, anyone want to do a smile?
I'm smiling.
Okay. No, my glasses are off. I can't see if you're smiling.
Oh, got it.
Well, I thought you were so overwhelmed, you have to take it.
I'm just saying, you want to do a second photo of something that's not just everyone standing there, is what I'm saying. Okay.
All right,
I'm
thank
not
you.
the shortest.
Who's the shortest one?
No, I'm not.
We
Eliza.
don't need to identify the shortest person.
Come on, it's always important to know. There's certain tasks that you need the short people for, like out in front.
Just come. Yeah, he's right here.
How to get this
This is
I was told not to touch the screen.
Yeah, I got you.
Yeah,
It's fine if you do. I need to know because I guess that's the sound.
right.
Yeah.
Yeah, thanks for letting me,
Nice suit.
Oh, thanks.
Nice jacket.
It's from Banana Republic.
is there any way to, is it just?
Drop it.
Remember the whole title of what we're doing? The paper?
I don't even remember the current title.
No. The thing is, you'll see the current title.
All right, so let's start up the afternoon session. The first talk is going to be given by Alex, who's an undergrad at Tulane, who has been working with Dennis as well, and he's going to speak about moving towards a quantum theory of entropic gravity. So, thank you.
Thank you. So, as Dr. Glasser mentioned, my name's Alex, and I've been working on this project with Dr. Bondar for a little under a year now, and just like to share with you what we've been working on so far. So first, I'd like to distinguish between potential and entropic forces in general. I'd like to discuss Eric Verlin's one of his motivating arguments for entropic gravity. I'd like to bring up a very strong critique of entropic gravity that we then would like to address by modeling entropic gravity near Earth's surface in the context of open quantum systems, and then compare our results to those of ultra-cold neutron experiments. So traditionally, we think of gravity as a potential force. So a potential force is one dictated by a potential energy. In particular, the force is given by minus the gradient of the potential energy. Potential forces are by their nature reciprocal, so every action has an equal and opposite reaction. They're path independent, and they're also additive. Now, in order to try to find a theory of gravity that perhaps fits into the standard model or can explain things like dark matter, there have been new theories of gravity that have been proposed that pick up fundamental assumptions, one of which is a theory of entropic gravity. So an entropic force is a certain type of dissipated force, by comparison, which is emergent as a consequence of the second law of thermodynamics. So an entropic force is given by this equation here, where we have a temperature times the gradient of the entropy. Now, entropic forces are by their very nature non-reciprocal, they're path-dependent, and are not additive. So a great example of an entropic force is that of a rubber band. So a rubber band itself is made of polymers that, when unstretched, are in a, you could say, maximally jumbled state, and this corresponds to a state of high entropy. Now, when you stretch this rubber band out, the polymers themselves become more lined up with each other, and there are fewer states available, thus decreasing the entropy. Now, if you have a stretched rubber band in an isolated environment, then it requires no work or energy for it to return back to its unstretched state, and this is characteristic of entropic forces overall. So this guy, Eric Verlind, proposed in 2011 that perhaps gravity could be an entropic force. Now, one of his motivating arguments for this takes insights from black hole entropy. So Jacob Bekenstein here argues that, let's say we have an object of mass m that comes near a black hole, and he argues that when this object comes within one Compton wavelength, delta x here, of that black hole, that it is effectively absorbed. Now, before this object is absorbed in the black hole, we can for sure say that it exists. However, once it enters the black hole,
You mean the event horizon?
the event horizon, yeah. However, once it enters the black hole, we can't say whether it exists or not. So we've effectively gone from one state to two in this razor's edge argument, which corresponds to a constant change in entropy. So delta S here. And here we have a factor of 2 pi, which So then we can also consider that this object going into the black hole, crossing the event horizon, has some acceleration. And according to the UNRWA formula, we have an associated temperature that this object feels when it is accelerated. So overall, we have a relationship. We have relationships for entropy, this position, and temperature, which he effectively fits into the entropic force equation here and arrives at the familiar force equation F equals ma. Now this is just a motivating argument, and he has other arguments as well, but this at least gives some kind of insight into what he's working at. So almost immediately after he came out with this argument, there was a counter-argument saying, no, gravity is not an entropic force. And the major criticism here is that entropic gravity would destroy quantum coherence. So the argument goes, we don't see any Brownian motion for objects that reside inside a gravitational field. So what that means is that if entropic gravity is true, that small objects must be strongly coupled to this environment. Now, strong coupling, it's believed, causes decoherence and wave function collapse, which we do not observe in cold neutron or cold atom experiments. And so on purely physical grounds, some have argued that entropic gravity just cannot be true. Now, for our project, we've taken this criticism very seriously, and we've said, wait, let's see if we can actually make a model of entropic gravity and acting near Earth's surface and see what happens. So using insights from quantum reservoir engineering, we hope to describe entropic gravity in the context of open quantum systems. So what is quantum reservoir engineering? In general, the results listed in this paper here of quantum reservoir engineering are that we can, in the language of open quantum systems, we can create almost any dynamics we want for a quantum system by coupling it to environments. So in our situation, we can employ this to say, well, what if we treat gravity as just such an environment? That is, we treat gravity near Earth's surface as an environment in an open quantum system with its usual dynamics. What do we get? Well, for our analysis, we have two cases here: coherent evolution, which we describe in terms of the Lindblad mastery equation, and also entropic evolution, which we describe also in terms of the Lindblad mastery equation.
S is entropy in the entropic case?
No, S is actually a free parameter.
Okay.
S is not entropy. So in the coherent case, we have our kinetic term, p squared over 2m. We have our potential term, mgx, and this fits inside the commutator and is commuted with rho to get our dynamics. Now in the entropic case, we have the kinetic term here and no potential term. And in fact, we absorb it in this dissipative term, d. Now, what's unique about this dissipative term? Well, most strikingly, we have this free parameter s. And with this parameter s, we can effectively control how much decoherence takes place in our model. And then also x naught here is just a scaling factor.
I'm sorry, if I may ask a question. Is the free parameter here like a temperature, if you were to take an analogy with another kind of a reservoir?
So our free parameter here is just it's a real valued unitless parameter. So I'm not sure that it necessarily corresponds with temperature directly.
But it should have something to do with curvature or something like this. That's the only place gravity is coming in.
Well,
Through S.
Well, so our model is basically just modeling gravity near Earth's surface. So not accounting for like general relativity or.
But the only place I see little g, that's it. and then something in S. So little g is what is little g?
The gravitational acceleration
Oh, okay, good.
near
Thank
Earth's
God.
surface.
Okay.
Oh, sorry.
It's very close to the surface, fine.
Yeah.
And then S,
S is our free parameter.
oh, I understand. What is that modeling physically? This is physics talk.
So the thing is, both of these models satisfy the Ehrenfest relationships that are characteristic of gravity that we know. So the time
Independent of the value of S? No.
regardless of,
Really?
yeah, independent of S, because we're dealing with averages, right?
I see.
So we're saying that the average dynamics overall satisfy these Ehrenfest theorems,
Okay.
characteristic of gravity as we know it. So we have time rate of change of the position gives us 1 over the momentum, and the time rate of change of the momentum gives us minus mg.
And this x naught is just some characteristic length scale?
Yeah, it's just a scaling parameter. So x naught is just h bar squared over 2m squared
Oh, I
g.
see it, sorry.
Yeah. Yeah. Anything else? Okay. So when we take the asymptotic expansion so the limit as s becomes very large, what we effectively do is we're able to move mgx back inside the commutator here, and at least in this expansion it mimics that potential, and then we get this other term and this other term and higher order ones all proportional to 1 over s or greater. So what that means is the larger we make s, the closer we mimic coherent evolution. Now, digging a little deeper, when we perform the purity analysis, so purity is just trace of rho squared. If we take the time rate of change of that, what we've shown is that this is, in fact, a monotonically decreasing function of time. And furthermore, when we plug in the asymptotic expansion, we get that it is a function proportional to 1 over s. So again, as s approaches infinity, our purity rate of change approaches 0, and we effectively can maintain coherence for as long as we want. So entropic gravity can preserve quantum coherence, but how does it hold up to experiments? It would be the follow-up. So what we do is we compare our results, our theoretical results, to the experimental results from this paper here, where Rabi oscillations are induced for neutrons residing in gravitational quantum states. So the setup for this experiment is that in region 1 here, I'm not sure if that's very visible. In region 1, we have ultra-cold neutrons, so existing in the ground state and first few excited states in the gravitational field.
Whoa. Okay. So you have a reactor spewing out neutrons.
Yeah.
Okay. What do you mean by the first and second excited state of the neutron?
So, so when you calculate the energy eigenstates for an object of mass m residing in this gravitational potential, right? If you assume the potential model,
In free fall?
In free fall, yeah. Then you get energy eigenstates from that, and so they're cooled down to the ground state, something like, which is equivalent of like 1.4 pico electron volts, and then several higher energy states.
But if it's in free fall, why are the energy levels quantized? That's what I
Is this
understand.
quantum bouncing ball, like with Airy functions? And
Yeah, that's exactly it.
Oh.
Yeah.
It's in Sakurai's book on quantum mechanics.
Thank you. I have
Yeah.
a whole paper on the Airy function. Okay, so it's this Airy function level.
Right.
Okay.
Yeah. Yep. So.
Sakurai got it from my paper.
So we have these ultra cold neutrons that enter in region 1 here, and then in region 2 they undergo Rabi oscillations. So
where is this reactor?
it's not pictured here, but
Like where on Earth is it?
Germany.
Germany or Austria? Not a
I-
good question.
Street neutrons behave
The
differently.
big neutron interferometry facility is in Austria, but I wasn't sure.
The guy that does these experiments
Okay.
is from Germany, but maybe I'm
Never
I'm
drop
mistaken.
your cell phone into the nuclear reactor in Austria, I'm just saying.
Good advice. So these neutrons then pass through this area here where we have a boundary that can oscillate up and down with variable oscillation strength in millimeters per second and oscillation frequency in hertz. So then after evolving through region 2, it passes into region 1, and we effectively measure or count which neutrons are in the ground state by the end of this evolution. So we'd like to see, can our model get the results of this experiment? So in order to take our results already mentioned and match these, we need to account for two things. One, our neutrons have to bounce off of the boundary, and two, we have to make the boundary oscillate.
Because this is where the question of the area functions come in.
Right.
You have to have a boundary in addition to the gravitational potential to get the area function.
Right.
Otherwise, it's a continuous eigenvalue, not quantized. That was,
Okay.
there is a
yeah.
boundary. It's hitting,
They-
it's bouncing off something.
Yes, definitely.
Alright.
And so in our model, so we include this boundary condition here, and what we want to do is try to see if it can enter into the Ehrenfest relationships. And what we find is that in fact it does. So when we have this Hamiltonian here with the wave function psi, or the ket psi, and we calculate the time rate of change expectation value of momentum, then we get the usual minus gradient of potential in addition to this extra term, which here we have h bar squared over 2m, and then we have the derivative of the wave function evaluated at x equals 0, and then its complex conjugate here. But we can recast this in terms of the second derivative of the Dirac delta function, where we define that here. And this is really helpful for our analysis because then we can effectively treat this as an instantaneous force and include it in our Ehrenfest theorems. To add bouncing to our model, in the coherent case, again, we have the kinetic term, potential term, and we just include this extra part, treating it as a instantaneous potential that the neutrons experience. And then in the entropic case, we have the kinetic term, and no potential term, and we add the same boundary. Then the dissipator D here is not affected by this at all. So then the next step is to just say, okay, we have a boundary included in our dynamics. Let's just make it oscillate. So we effectively just do that by just adding this minus A, the amplitude of oscillation, sine omega t, omega being the frequency of the oscillation, and t being time. I'm sorry, this is messed up. I'm sorry, this is a mistake. This is from, this is actually what happens when you change the reference frame to that of the boundary. But
But the boundary is like some silicon or germanium surface or something, right?
Yeah.
Are you gonna make that
variable.
wiggle?
Huh?
How are you gonna make it wiggle?
Well, from my understanding, they have it separated here, and then I guess they make it
induce
yeah, they induce the oscillations. Yeah. So I get. Oh, whoops. So I apologize. This is not what I was trying to give, but ultimately, what we're supposed to get for the entropic case is we just add this oscillating barrier into the commutator, and the dissipator is invariant under the change of variables that we add. So now that we've developed a sufficient model to describe what's going on in this experiment, let's see what happens. So we have two free parameters in this experiment. One's oscillation strength, as I said, and the other is frequency. So first, taking a look at frequency, we have our measured data points here, the red dots, and then the red line here is the coherent evolution, which we listed in the previous slide for the coherent case. And then in green, orange, and blue, we simulate our entropic model with different S values. So green is S is equal to 1,000, orange is S equals 500, and blue is S equals 100. So what we see is that as we showed analytically, the higher we make S, the closer it matches the coherent evolution, which is good. And furthermore, when we compare our entropic models to the data listed, we see that S is equal to 100 seems too low of a value, there's too much decoherence taking place, and so we would say that it would probably have to be some higher S value if entropic gravity is to be true in this case.
Increasing S means it has less effect, right?
Yeah, so
Okay.
increasing S means that there's less decoherence.
Okay, okay.
So yeah, and so we see that there are these dips here, and these correspond to driving the Rabi oscillations at resonance. So this first one corresponds to driving from the ground state to the second excited state, and the second dip here corresponds to driving from the ground state to the third excited state. And so let's see what happens when we fix the oscillation strength, fix the frequency at the first transition, omega 02 I call it, and then vary the oscillation strength. So as we can see, again, the higher we raise S, the closer we get to the coherent case. And also, other than this extraneous data point, we seem to have a pretty good fit for S equals 500 or greater, qualitatively speaking. And then if we do the same thing for the second oscillation, where it's omega 03, so transition from the ground state to the third excited state. Again, we see S equals 100 falls out, but we see that S equals 500 seems like a pretty reasonable lower bound on this S parameter. And again, we get that the higher we raise S, the closer we get to coherent evolution. So overall, what have we seen? We've shown that entropic gravity can both maintain the strong coupling and also minimal decoherence. And we can make S as large as we want in order to mimic conservative gravity as much as we'd like. Furthermore, qualitatively, our models seem to match results from these ultra-cold neutron experiments, and we would probably estimate that S has a lower bound of about 500, although we need to conduct some chi-squared analysis and see what perhaps an optimal S value would be. Looking forward, we'd probably like to expand this model to gravity beyond Earth's surface, and also try to simulate results from more precise cold neutron experiments, such as like Ramsey spectroscopy. So thank you very much for your time.
Is there a value of S that corresponds to Verlin's theory?
So Verlinde himself has not proposed any full quantum mechanical model of entropic gravity. A lot of, yeah, so no, not yet. I don't think so.
I have a follow-up question. Can you go back to the slide where you were showing the dynamical equations?
Yeah.
This is
Four.
good, yeah. So I'm trying to understand where the d hat comes from. This is where you're saying you're modeling gravity as an environment, and is that that's right, right?
Yeah, more or less, yeah.
And why does this particular form emerge as the choice for the dissipative dynamics? I mean, I understand the coherent case, it's just the usual kind of thing.
So,
when you plug it into the error test there, it reproduces the same ones in the coherent case. So it kind of fixes what the dissipator is to be.
This is a unique choice.
I think so. Oh, I mean, like.
so it's not necessarily unique. So let me go back to
Is it like
the
unique
first
up to
slide.
S or like?
So this doesn't necessarily have to be unique. So in quantum reservoir engineering, you can effectively add as many environments as you want, and we could have modeled gravity as being like many environments. This is just the simplest case where we just have a single environment, a single dissipative term that works into it.
Why exactly do you call it entropic gravity? It seems like some kind of environment gravity, or I don't know.
So we haven't, so
It's just because like dissipated?
yeah, so basically like gravity would be a dissipative force itself, but I mean this is more just working with like, without having a broad reaching theory of entropic gravity, you know, can we address this criticism itself by saying, if we look at gravity just at Earth's surface without saying like this is how the entropy is related and all of this, like does this criticism hold water on physical grounds? And we say, no, it doesn't, based on these results.
So the vibrate, what temperature is this being carried out at, the experiment?
I'm pretty sure, so the neutrons are at the scale of like pico electron volts themselves,
Okay.
like in terms of energy levels, so I think it's around that level of
Like how are they interacting, I guess, with the mirror is my question. Let's say if you were to do something else like superfluid, how would that change the?
How does the boundary change?
Yeah.
I don't know. I don't know. I think that this boundary itself was selected experimentally,
Okay.
so that there's, you know, it's a perfectly elastic collision, or as close as we can get.
Sure.
But that's all that I know.
You might want to check out the book by Gregory Wolovic, The Universal Helium Problem. Might be exciting.
Okay.
When you say you want to go beyond Earth's surface gravity, what exactly do you mean by that?
So, I mean, the general equation for gravity is not, you know, F equals minus mg. It's F equals.
So you have to change the scale of your quantum experiment, right? So it has to be like a large scale quantum experiment to deviate from that simple behavior.
Yeah. Yeah. So I mean, like, I guess for modeling purposes, it's like when we have the minus mg, then that itself is like translationally invariant. So one obstacle for like modeling things beyond Earth's surface is that we no longer have that translation invariance. It matters like where you're located as to what free fall looks like. So I guess does that answer your question?
Well, so I mean, so deviation. So the mg times x is just the first term in the expansion, right?
Right.
So in my view, you would have to have either really precise quantum experiments or looking at it over a very large scale, so where you get noticeable changes or deviations from this mg, right? Or yeah, that's.
Okay.
So I'm still flummoxed by S. Okay, so in your last slide you say you get, your data's consistent with like S is greater than 500.
But qualitatively, yeah.
Right, so, which is consistent with S is equal to infinity, which means no effect. Is that correct?
Well,
Your data is consistent with no effect at all.
well,
Put a bound on it.
well, so.
You have not seen entropic gravity in this experiment.
So essentially we're saying like, so if we take S to be infinity, we can mimic coherent evolution as closely as we'd like. But if there is so let's say, you know, we exhibit some experimental error. Well, it could be that part of it, if entropic gravity were to be true, let's say some of that experimental error is actually related to, you know, slight variations from the bath itself, like the.
But when I think in terms of a bound, this greater than 500 is consistent with no effect. Correct?
In this model, yeah. So.
Okay, I'm just saying, so you have not shown any sign of entropic gravity in this experiment.
Yeah.
You'll put a bound on it.
Right, but so all we're saying overall is that we can't rule out entropic gravity on the grounds that it destroys decoherence, because this in fact is a model where coherence is preserved.
And so what is the role of mass? Let's go back to the equation, because the puzzling thing is whenever you have something that looks like e to the I over e to the I times, okay, down there, e to the I x hat over x naught, and s is getting very large, so the exponential is going to 0, but it's actually in the complex plane, so it can go into 0 on many different contours, and so that's all really weird, okay? But mass out front, so if mass was bigger, does this work better?
So yeah, so if the mass is larger, the thing is, if we take the, I'm pretty sure when we take the asymptotic.
Yeah, S has to be larger, I think, right?
Huh?
S has to be larger if mass gets bigger according to.
So if I gave you a neutron that weighed several hundred times more than a neutron, you could rule it out at a better level, you think?
Well, I think that it's actually related to being lighter.
So lighter is, I'm just asking, if I want to redo the experiment with a different particle, electron would be better, or a uranium atom would be better?
Well, I don't know.
They've done these experiments in France where they drop ultra-cold atoms from a magneto-optical trap onto an evanescent light mirror, and they see the same Airy functions get excited. So, but the mass is that of an atom instead of a neutron, so it's like, you know, I don't know, cesium, how many neutrons in cesium?
We're gonna have to end it on that question.
You know.
Thank you, Alex.
Very good mind.
It was a good comment.
Thank you. I'll leave this here.
And next up is Professor Sheehy from LSU. That's right. We're going to talk about Majorana fermions.
So, how do you say this, Dan? Majorana or?
I say Majorana, but I could be wrong.
What do you say?
How do you say it?
The other way is like Majorana.
It's actually Majorana. It's a G-L-I. So people either say Majorana or Majorana. It's actually Majorana. It's not marijuana, which is the temptation. The marijuana part. I give up, Mark. Who is Ole Baggins and O markers?
You were holding a bag of markers.
So this will advance it.
I had no idea what you were saying.
And the bottom one.
Bilbo Baggins, whether he's Dr. Ole Baggins.
Baggins or markers.
Awesome, okay.
Very obscure.
All right.
It's necessary.
So we're going to now hear about chiral marijuana fermions in condensed matter.
Majorana.
That's right, chiral Majorana fermions in condensed matter materials. So thanks for inviting me here. So I'm going to try to make a connection between the subject of this workshop and what I work on, which is condensed matter materials. So this work was done in collaboration with David Elsbaugh, who is here in the back. There's David. So and also Mark Gorbeg and Pascal Simon. And we have a preprint that just was submitted a few weeks ago, and it's submitted. It's under review right now. So what I want to talk about today is topological quantum computation. So that's the motivation for what we're going to discuss. And you might have heard a recent article in Wired magazine pointed out that topological quantum computing has long been a beautiful dream.
You've been stalking me.
Two top scientists are now facing off over whether it will exist by 2030. It's funny when I see that, I think it's more than 10 years in the future, but yeah, it's right around the corner. And so this is the two top scientists in question were John Preskill and John Dowling from LSU. And so I guess the bet is, so you claim that there's going to be no topological quantum computation within 10
There
years,
will
right?
be no demonstration of a 2-qubit gate.
I see.
In
Very
any
precise.
system, and
I see.
before March 1st, 2030.
Okay. So we'll see. So I'm definitely not going to present that. What I'm going to do is I'm going to discuss one possible.
We didn't even ask what the bet was for. It's a
Yeah.
pizza and a beer.
Oh yeah, it's a pizza and a beer. I saw that from the
That's the
article.
important
It's
part.
what kind of pizza or beer?
Yeah. New
Not
York,
defined.
New York pizza, the Chicago pizza is lasagna.
So one way to achieve topological quantum computation that's been proposed is to use what are called Majorana fermions. So essentially, one way to think about it qualitatively is that a Majorana fermion is like half of an electron, and that sort of makes it immune to decoherence. The first possible use of these is through what's called a Majorana zero mode. So I'll discuss those in some detail. So the Hilbert space associated with these Majorana zero modes is very large, and theoretically it should be possible to braid these to implement quantum operations and solve this bet. Unfortunately, experiments have found this braiding to be exceptionally difficult, so it's very difficult to actually do this in practice, which has led people to pursue other options. So these other
And by
options
difficult, you mean impossible.
that's right.
No one has demonstrated this in any system
No.
whatsoever.
They've seen evidence of Majoranas, but not braiding. Yeah, it's definitely very difficult. So yeah, I should upgrade this difficult to impossible probably. But I mean, you never say that because it could be that the experiment will be done tomorrow.
Yeah,
You never know.
that's what the bet's all about.
That's what the bet's all about, exactly. So there's a new type of chiral Majorana, new type of Majorana fermion called a chiral Majorana that, in principle, is easier to braid. And so this was proposed by Shuqing Zhang and co-authors in 2018. And so I won't talk about this device in detail, but basically it's some kind of condensed matter interferometer device that can implement the same type of braiding operation that's shown in this cartoon here. So our work is sort of on the condensed matter side. We're interested in Majorana fermions, chiral Majorana fermions in topological superconductors. And what we find is that these Majoranas are accompanied by additional low energy states. So essentially, even these chiral Majorana modes, there's other low energy states. And one question is, how will these additional states impact quantum operations? So, and this is sort of our question for the future. So, okay, so I'm going to review Majorana fermions. The first thing I want to start with is conventional fermions. So what I mean is electrons, right? So the way we describe conventional fermions theoretically is through creation and annihilation operators that are similar to what you have in the quantum harmonic oscillator. So we have a creation operator that this creates a fermion in quantum state I, and we have an annihilation operator that annihilates a fermion in quantum state I. So these operators allow us to express any many bodies wave function in terms of acting with these operators on the vacuum state. So here's some wave function, and as an example, I've put two fermions in this state. So we have a product of creation operators acting on the vacuum. So this is just to set up the notation. So we know that identical fermions have a minus sign under exchange. And this minus sign is encoded in the algebra of these operators. Okay, so for example, you can essentially, one of the algebraic relationships is that psi dagger is a delta, a Kronecker delta function minus psi dagger psi. So this minus sign is exactly the minus sign for fermions. It's the Pauli exclusion principle. A related statement is that psi I dagger psi j dagger is minus psi j dagger psi I dagger. This is the Pauli exclusion principle because if I set I equal to j, I get it must vanish. So psi I dagger vanishes. So this is the Pauli principle. And what I'm trying to get across is that once we know this operator algebra, these rules, that sort of tells us how to, tells us everything we need to know about these fermions, or a lot of what we need to know about these fermions. So, so now what I want to do is describe Majorana fermions. So Majorana fermion is half of a fermion, half of a regular electron. So, okay, so how do we do that? Well, we're going to split the fermion creation and annihilation operator into real and imaginary parts. Okay, so even though they're operators, I can still sort of say, well, let's write this psi as 1/2 a different operator, gamma, plus I chi. So gamma and chi are new operators. They're real in some sense. And I can define psi dagger as, if I take the adjoint of this, I get gamma minus I chi. So this gamma and chi operators, these are Majorana operators. Okay, so if I invert these relationships, if you look at these, it sort of says that these are real, right? So if I take the adjoint of these, by construction, I get the same thing back. So these are charge neutral operators that can describe Majorana particles. And the question you might ask is this useful for anything? It turns out that there are systems that can exhibit these types of Majorana excitations. So, okay, but before I get to that, I want to describe the Majorana algebra. So we have the algebra for fermions on the previous slide, and so we can just derive the algebra for these Majorana operators. You just plug into the previous formulas. And so the second says that 2 of these is equal to 1. So gamma is 1, and gamma chi is minus chi gamma. So this is sort of the Pauli principle. Okay. So if we generalize this to many Majoranas, we get, this is the Majorana algebra. Okay. So are there any systems where this splitting is useful? So the answer is, in principle, yes, but as we've been discussing, it's not clear how to actually observe the braiding that we discuss. So, but in some sense, the first realization I'll discuss are so-called Majorana zero modes. So this is when the wave function associated with one of these Majorana operators is localized in real space. Okay, so that's what I'll show on the next slide. So the one realization is inside the core of vortices in P-wave superconductors. So, okay, so let's discuss P-wave superconductors. So a superconductor, just really briefly, I'll have to go really quick through what a superconductor is. It's a condensate of electron pairs. These electron pairs are called Cooper pairs. And a superconductor has no available low energy states. And one way to think about that is because all the electrons are formed into these pairs, and that means that there's no available states. That changes if you put a vortex in a superconductor. So a superconductor can have a vortex in it. It's a topologically protected excitation. It's essentially a hole in the superconducting condensate. So one way to create these vortices in an electronic superconductor is to apply an electric field. It also happens if you rotate a superfluid or a superconductor, you'll make vortices. Okay, so, and what I claim is that these vortices can host these exotic Majorana particles. So, okay, so here's a classical vortex, not a quantum vortex. We had these in Louisiana.
Quantum meteorology.
That's right. Here's some quantum vortices. So these are rotating BECs from Eric Cornell's group at Gila. So these are not in a charged superfluid. This is in a neutral Bose-Einstein condensate of rubidium, but these are quantum vortices. So to make a Majorana fermion, you can't just use vortices in a BEC or even vortices in a regular S-wave superconductor. You have to use a funny type of superconductor called a P-wave superconductor. So, however, so vortices can always have low energy states, but they are only Majorana fermions in the case for P-wave superconductors. Okay, and this was first shown in 2001 in this article. So, okay, so I just want to briefly discuss Majorana zero modes in vortex cores. So here's my cartoon picture of a P-wave superconductor, and I'm not going to prove it, but I'm just going to tell you that there are Majorana states associated with each of these vortices. So that was shown by Ivanov, and also, there's a related article by Reed and Green that I didn't include the reference, but I can get that reference to you if you want. Okay, so just to be clear, the green is just my superconductor. And these are my pictures of vortices. Each vortex has one Majorana. Okay, so what that means is that it can host one Majorana fermion. Okay, the other half of the, so you know, a Majorana is like half of a electron state. The other half is in another vortex. It can be any other vortex. Okay, so if you add, so there's no such thing. So outside of this superconductor, there's no such thing as Majoranas. It's like an emergent excitation existing only in this system. So if you add a real electron, it has to split up and go into two Majoranas. In some sense, it's like saying the electron wave function is sort of split between these any two of these vortices. Okay, and there's many ways to do this. So I've sort of drawn a cartoon here. So I've imagined that there's one electron associated with these two Majorana vortices, one electron associated with these two, etc. So here, you know, if I have 8 vortices, there's, you know, electrons in every possible pair. And you should imagine there's, you know, the quantum aspect of this is that there's many possible ways to do this. Okay, so, you know, roughly speaking, regular electron states are stretched between these two vortex cores. Okay, so how big is the Hilbert space? Well, that's a good question. So if we have 2n vortices, each pair of vortices either has 0 or 2 Majoranas. So either has 0 real electrons or 1 real electron. 1 real electron is 2 Majoranas. And these are degenerate states. They're both at 0 energy. And so we have a 2 to the n dimensional Hilbert space. Okay, so that's analogous to having n qubits, if you want to think about it like that. And if we want to implement a quantum operation, so you're supposed to imagine that the way these, if they could braid these, which they can't, as we've discussed, but if they could, they would pair the system with, by putting electrons in certain pairs of vortices, and then they can braid the vortices, and then they can try to measure them, do a measurement at the end. Okay, so this braiding is a non-abelian process, and I'll discuss the braiding in more detail in a subsequent slide. And the way you would read it out is that you bring pairs of vortices together. So if I have a pair of vortices that's far apart, so basically they're only truly Majorana states when the vortices are far apart. If you bring them together, the Majorana states on these two vortices essentially hybridize, and that they're no longer degenerate, and you can measure the difference between having 0 or 1 states on that pair of Majoranas, and you can measure that. So basically, if I bring a pair of vortices close together, I can detect whether that pair of vortices has an electron associated with it or not. Okay? Is there a question?
How are they, I mean, I guess maybe this is where the topological superconductor comes in. These are vortices, they're not interacting. This isn't a Kosterlitz-Allis phase. This is a Rose-Glass.
No, it's not a Kosterlitz-Allis phase. We're just imagining we somehow prepare vortices and we're able to control their location in space. And that's what makes it experimentally impossible.
Yeah, sorry.
Is that they, what's that?
I just apologize.
Oh, that's no problem. Yeah. So you're supposed to imagine that essentially if I combine any pair of these vortices, then I can measure whether or not there is 0 or 1 fermion in there. And that's sort of a quantum measurement, meaning that I could get, you know, I'll get 0 or 1, but well, I'll discuss that in a little bit more detail. But essentially, what I want to say is that you can measure this, we're claiming that you can measure this level occupation and therefore measure the state of the system after braiding them. Okay, so I wanted to discuss next how this braiding would work in principle. So, so the braiding operation, so we want to define a braiding operator to act on our Hilbert space, this Majorana Hilbert space, and it must obey the rules of the braid group. So, so imagine I define a quantum operator, T hat, that braids vortices I and I plus 1. So here are I have 4, these are 4 vortices, and they may or may not have a Majorana state in them, and I want to think about braiding these states. So how would I braid them? Well, so what I could do is, and here's time. So what I can do is I can take this blue one, move it here, and move this red one here, so I can braid on the left. And then I can subsequently braid the vortices that started at positions 3 and 4. Okay, so I can have this braid operation. I braided these first, and then I braided these first. So it should be obvious that if I do the braiding in the opposite order, I'll get the same thing. So here I'm going to do the opposite order. See, here I start with 4 vortices. Now I'm going to braid 3 and 4 first. and then I'm going to braid 1 and 2. And what I'm trying to show here is that because I braided vortices that were separate from each other, there weren't any vortices in common. Essentially, these are equal. These operations are the same. That means if I can define a braid rule, T1, so that it goes from right to left, so T1, T3, that's here, so I braid these two, then I braid these two, is the same as T3, T1. And that shows that these operations commute when braids involve separate vortices. Okay? So
this
yeah.
is the point where I go, how do I see the non-abelianness from staring at this?
It's coming.
It's coming, exactly.
Alright.
So this is abelian, exactly. So this
That's
is
what I'm
abelian.
doing.
Yeah, exactly. So this part is abelian.
And so this cannot be used to make a quantum computer.
Well, I have to braid adjacent. I have to do more braiding.
I thought abelian was out.
No, abelian things don't make quantum computers.
They don't, but this is only one type of braiding.
Yeah.
So basically,
What
I
else to get to?
have to go to the next slide.
I'm just,
Yeah,
I got
yeah,
a
there
pizza
you
and a
go.
beer riding on this. Yeah, but, I need to know. All right. I mean, I might not be around in 10 years.
No, that's you'll be around. We're gonna let's do more braiding. What about operations that share a vortex? They could be non-abelian. So now I'm going to have 3 vortices, and I'm going to first braid on the left, then I'm going to braid on the right. So here's time. So first I braid vortices 1 and 2. Then I braid vortices 2 and 3. So now I've braid these, and now I braid again the vortices that started at positions 1 and 2. Right. So just to be clear, 1, 2, and 3 don't move. So a braiding operation, between 1 and 2 always braids the first. Okay, so this is a braiding operation, 1, 2, 2, 3, 1, 2. Now what we can do is we can do another braiding operation that gets the same answer. Okay, so if we instead braid vortices at 2 and 3, then we braid at 1 and 2, then we braid at 2 and 3, we end up at the same state. So this state is the same as this. So these are equal. These two possible sequences of braidings are equal, but they it's non-commutative because you can see that this rule, this braid rule, wouldn't be satisfied if I was able to, if these operators commute. So basically, this shows a non-commutative nature of braiding operations that share a vortex. Okay, so this is the second braid rule. So these 2 braid rules are sufficient to obtain this operator in the case of Majorana fermions. So this is the part that's non-commutative, this type of braiding operation. So we've derived 2 braid rules, and if I generalize them to n vortices, because of course we want to do this for the case of many vortices, right? So we have 2 rules. One is that they commute if they're not nearest neighbors. That was that case. And if they are nearest neighbors, if there's vortices that, if we do braiding operations that involve the same vortex, then we have this braid rule. Okay? And so now the question is, how can we define an operator for braiding Majoranas that obeys this algebra, right? So we have to define an operator T that involves those gammas that I defined that obeys these 2 rules, right? And so, and remember that what we know about the Majoranas is that they obey this. What Ivanov showed is that a representation for that is given by this operator. So this says that this describes the effect of a braid operation on pairs of vortices. So let's see how this can work on a sequence of Majorana 0 points. So so far we haven't defined whether these Majorana states are occupied or unoccupied, but we're going to do that next. So let's prepare a system in a simple product state. So meaning I'm going to start out with these 4 Majoranas, and now I'm going to put 1 electron in the first 2 Majoranas. So my initial state is 1, so that just means 1 fermion in Majoranas 1 and 2, and 0 and 3 and 4. So product state. Now I want to, and if I was to read out, I would get, if I was to read out in 1, 2, and 3, 4, I would find, the way I would read out is I would bring 1 and 2 close together, and 3, 4 close together, and then the claim is that I would be able to detect whether or not there is a fermion in this state. So I would measure 1 for this pair and 0 for this pair. So that would be the readout. Okay, but now, instead of doing the readout, let's try to braid these. And so the simplest braid that you can do is to braid 2 and 3. So let's braid those. Here's time. So now I bring 3 here and 2 there. And now my final state essentially has this, remember the blue line is a real electron, but that electron is distributed between these 2 vortices. So now if I define my readout to measure 1 and 2, okay, let me just slow down. So the final state is a braid operation on the initial state. So if I take this initial state and I act on it with the braid operator I defined on the previous slide, I'm skipping all the details, but the answer is that you get a state like this that's intrinsically entangled, right? So this says that if I was to look at the state associated with 1 and 2, it's in a superposition of being that this is occupied and 3 and 4 are unoccupied, and 1 and 2 being unoccupied, and 3, 4 being occupied. Okay, so it's in a superposition. What that means is that if you were to measure, if you were to essentially do a readout by bringing 1 and 2 together, the same readout, you would have an average occupation of 1/2 for 1 and 2, and for 3 and 4. And we see that we were able to create an entangled final state. So this is the rough picture for how braiding would work if it was possible to do this in an experiment. Okay? Unfortunately, as we've discussed, it's really hard to do this. So experiments have not achieved braiding in condensed matter experiments. Part of the problem is it's hard to have a P-wave superconductor. There's very few of them. There's other setups, however. There's other experiments that can achieve Majorana zero modes. They also haven't braided anything. So here's some theoretical setups. This is a good review article by Jason Elisea. So essentially this involves junctions between topological insulators and other materials. I won't go into the details, but basically the Majorana zero modes are essentially at the ends of various, here's a gate, there's a Majorana zero modes at the ends of this gate. They would be localized there. Experiments have observed Majorana zero modes, or claimed that there's evidence of them. So if you take an S-wave superconductor, and you put a wire on top of it, and you have an external magnetic field, they essentially can measure these tiny little peaks in the conductance and see evidence of Majorana states at the ends. So you can't, anybody see there's like a purple dot right there on the ends? That's supposed to indicate the existence of the Majorana, but the problem in this setup, so there's evidence, oh thanks.
Is it visible there?
I still can't see it.
I'm fine with
you know.
this.
I can see it.
I trust you.
I can see the platform.
They're there, but how are you going to braid them, right? They're there, but it's too hard to braid these because they're.
We can just kill the ones over the stage and none of the others.
Yeah.
Can you do that?
The spotlights are something.
It's all right.
Right, you turn
Yeah.
the house off the spot.
The problem, but this was just a warm up to say. So once again, so even if you could see they can get these Majoranas, but they haven't been able to braid these in experiments. That's still the problem. So this brings us to what are called chiral Majorana fermions. So chiral Majoranas are an itinerant version of the Majorana fermion. So itinerant just means they can move. So it's
I have a peanut gallery question, sorry.
Oh, yeah.
I mean, is the peak unambiguous? I remember there'd be quite a bit of debate about how smoking gun that little peak is, you know what I mean?
Oh, it's very, yeah, there's a lot of debate over whether this could be some other low energy state. There's always the possibility of other low energy states that could.
And none of these papers are by anybody at Microsoft?
There could be co-authors from Microsoft.
The one thing you have is from UMD, not Microsoft.
And because what I heard was that they see evidence, but the people dispute the evidence of that's these peaks.
Yeah, no, there's a lot of debate about whether they're actually Majoranas. But even if they were, you still can't braid them. So that's the further problem. So there's a question of whether they're actually Majorana fermions, and there's been a lot of proposals on how to solidify them. But I mean, sort of the only way you can really be sure is to actually find an experiment that would allow you to braid them and show experimental evidence of that. The hope is that chiral Majorana fermions, which are a different type of Majorana, they will be easier to braid. They're itinerant, they are charged, so just like Majorana zero modes, They are charge neutral, low energy electronic state, and the claim is that they would be easier to braid. So essentially they would be intrinsically mobile. They would exist in some kind of conducting channel. So here's a cartoon picture of a type of device that would possibly braid chiral Majoranas. So, and this is proposed by Zhang and collaborators in 2018. So recent experiments have shown evidence of chiral Majoranas, and this is where we got involved in this project. So essentially the experiment was done by Menard and collaborators, involved essentially a superconductor with a bit of cobalt on top of it. The cobalt is magnetic, so this is superconducting lead. And then we have a cobalt island on top of it, and that cobalt island essentially is what causes the Majorana states to form, the claimed Majorana states. And so this is where we got involved. So we're condensed matter physicists. So we were just interested in understanding the results of this experiment. And how we could possibly, so going forward, we want to know how we can possibly use these chiral Majoranas for quantum operations. So what they observed in the experiment is they observed a spatially localized state near the edge of the cobalt island. So essentially what we're showing here is the tunneling conductance is a function of position, and there's a ring here, and this ring is claimed to be associated with the edge of this cobalt island. Okay, so they observed this in scanning tunneling microscopy, and the possible claim is that there's this chiral Majorana fermion going around the edge of this island. So what is this state? So superconductors are typically gapped at low energies, as I briefly mentioned before. Roughly speaking, magnetic fields are detrimental to superconductivity. So roughly speaking, what's happening here is that the magnetic field is sort of suppressing superconductivity near the edge of this and leading to a Majorana state. So it's a bit more complicated than that, and I'll get into the details in a little bit. So I'm not sure how much time I have. Probably
4 minutes.
4 minutes?
Yep.
I started late though also,
That's-
but okay.
that's
That's
10
even
minutes late.
including that. Okay, I better go faster. Okay, so I can finish in 4 minutes. So here's our model Hamiltonian. It has a lot of terms. I guess I won't be able to describe all the terms in all detail, but essentially we're describing a superconductor with spin orbit coupling and a magnetic exchange field. So this is the effect of the magnetic island. And essentially what happens is that in this magnetic field, because of the existence of the island, is spatially variant. And so there's a point in space where the local gap in the spectrum goes to 0. So essentially here I'm showing the gap as a function of various magnetic field values for the case of a homogeneous magnetic field. And so the claim is that due to this spatially varying magnetic exchange, the gap in the spectrum goes to 0 at one point in space. So within our model, we model the spatially varying magnetic field to be linear in space. So here's our spatially varying magnetic field due to this cobalt island. And then essentially there's a topological transition between a large magnetic field region, which is topologically non-trivial, and a small magnetic field region where it's topologically trivial. So what you're supposed to imagine is that this spatially varying magnetic field is what creates these Majorana fermions. And so a top view of this setup would be, I want to emphasize, we're not describing a circular island, we're describing sort of a spatially varying magnetic field that increases in the y direction, as I've shown here, and there would be 2 parallel propagating chiral Majorana modes in this device. So the effective Hamiltonian for each of these chiral Majoranas looks like this. So it's a bit more complicated than the Majorana 0 mode case, but is still described by these real operators chi. I'm going to skip over this slide because I'm running out of time, and I want to describe our results. So we essentially just study a topological superconductor with a spatially varying exchange field. And what we find is additional low energy states. So we were trying to understand this chiral Majorana mode, but what we find are additional low energy modes that go beyond this, are in addition to this chiral Majorana. So the chiral Majorana, so this is the energy versus momentum for the states that we find. So here's the chiral Majorana, it has a linear energy momentum dispersion. here's all these additional states that are called Volkov-Pankratov states. These states are not quite located at the, this is a picture essentially of the wave function of the Majorana zero mode. It's localized right near this transition between the topologically trivial and non-trivial regimes. These Volkov-Pankratov states are split away in space, away from this Majorana zero mode. One thing that we're interested in is how they would detect these VP states in an experiment, and they could do it via a spin-resolved tunneling. So what you're supposed to notice is that this would be the tunneling density of states as a function of position and energy, and this is showing the splitting as a function of position of these Volkov-Pankratov states. And the point is that if you tunnel only one spin state of electrons, you get a very different picture for the tunneling Gauss. So this cross-shaped, so the last thing, one thing I want to mention is that this, I told you that we were motivated by these experiments. These experiments also found additional states, low energy states. So the experiments measured, so I told you the experiments saw evidence of chiral Majoranas. They actually found additional states that were not understood. So this is the data, the experimental data as a function of energy and position, and essentially this X shape here is reminiscent of what we find in our calculations. So we think that what they may be seeing in these experiments are these additional VP states. So future work is we want to understand what are the implications of these additional low energy modes for things like how we would use these chiral Majoranas for some kind of quantum experiment. So to conclude, we've discussed Majorana fermions. Majorana zero modes were the hot thing 10 years ago. In principle, they should work, but it's difficult to braid them. There's a new type of fermion called a chiral Majorana mode, a new type of Majorana mode that could be braided in an interferometer device, meaning just by passing a current through some complex device. Recent evidence have seen evidence of these chiral Majoranas, but they also see additional low energy states, also shown in these pictures. And our theoretical work finds that generically chiral Majoranas are accompanied by additional VP states. These additional states, these may be bad for doing quantum computing. So I guess this says that maybe John Dowling is correct. Maybe these additional VP states are going to make things more difficult for actually doing quantum operations with chiral Majorana modes. And one thing I didn't need to mention is we've studied other properties of these low energy states. And so if you want to see more about these, you can see our paper with David. Thanks.
Yeah, one question. So which, in that tenfold way or whatever, which classification is this that you're studying?
Oh, the topological classification system? That's a good question. In the tenfold way, isn't this, so it's a topological superconductor, so isn't this a D3 class, I think?
Okay. And then, so you guys are actually, you're taking some type binding model and you're doing kernel polynomial or something to find the density of states? How do you find the density of states?
Oh, it's an analytic model, and essentially, yeah, so it's not a type binding model, it's a continuum model.
Okay.
And yeah, so you'd have to look at our paper or talk to David if you wanted to know more about that calculation. But yeah, it's an analytical model.
All right.
But now we're heading into coffee time.
So what's the temperature of these experiments? Do you have a temperature in your model?
Okay, the models is zero temperature, and the experiments are not at zero temperature, but they're very cold. So David, do you know what the temperature of the experiments
I'm
is?
remembering 3 millikelvin.
Millikelvin.
Yeah, it's in the millikelvin. Yeah.
Okay, so at millikelvin temperature for superconducting standard IBM or Google qubits, the coherence time is on the order of maybe nanoseconds.
Mm-hmm.
So one of the things is that your gate speed should be several orders of magnitude faster than your coherence time.
Mm-hmm.
But I believe for the order of picoseconds for the gate speeds for standards, how fast can I braid? I need to be able to do lots of braids per coherence time in order for this to work, even if it works.
Okay, so that's a really good question. So here, the thing that I didn't discuss is how the braiding would work with the chiral Majorana. So instead of physically moving them, the chiral Majoranas, it would be electron, essentially current. It would be the natural electron flow at the Fermi velocity that would implement the braiding. So the braiding would be conducted through passing current at some complicated device. And so that's what makes this better is that it's easier to braid fast.
You don't have to actually move the things, but still.
Yeah, you're not physically moving them through some.
But you know, if you could come up with this gate to coherence time ratio,
Okay.
I mean, if that sucks, it doesn't matter if I can't braid or not.
Exactly. Exactly.
I think the
So.
coherent time will be a little bit, few orders of magnitude larger if you temperatures at the order of Kelvin. It's my
Well,
guess.
I know that if for the Google machine, it's 1,000 gates per coherence time. And I think that they do about, the gate speed is picoseconds.
Oh, okay, that's,
So that's where I'm getting the nanoseconds from.
So, yeah, we would want these electrons
Within
to
an
move
order
at
of magnitude that's approximately correct. So you need to be able to braid these at picosecond speeds.
Okay, that sounds fast.
I know,
They
that's
move,
what
they
that's
move,
why I brought it up.
you know, electrons in a wire go, you know, 100th of the speed of light, so that's, you know, yeah, that's fast. But, yeah, we would have to look into that in detail.
Yeah, I mean, that would be an interesting number, because
Yeah.
if that number is bad, then you might as well just give up now and I win.
You get your pizza.
Yeah, I eat my
Yeah.
pizza and go home.
We will find out in 2030.
Yeah.
No.
By 2030.
Yeah, at most.
Yes, at most.
It's sort of like the S parameter, right? It's 500 or less, right?
Well, let's thank Professor Ishii again.
Thanks.
And we'll stop the break for 15 or so minutes.
Mark, have you heard from Scott? When he's coming in?
I haven't checked my LSU email.
Either, well, I haven't, I don't see anything.
He said he was arriving late. That was the latest.
Okay,
That
so
was like
you don't have to be
the-
there, or you're going to post
I'm
it.
gonna come from. Sure.
You would host it, it's easier for you to get removed from Ron.
Okay.
Come on, I meant if I give her a receipt. I will.
That was awesome.
Oh, that was an awesome talk.
Thank you.
That was an awesome talk.
Yeah, great question, John. Appreciate it. Yeah.
Thanks a lot.
No, I should be invited. I did my best to connect.
How did you know about the deck? You were stalking
Because he posted it on Facebook. I mean, I do stalk your Facebook, so.
But you know, one of the things I looked
Also
up.
sent him an email.
Oh, thank you. Yeah.
Just make sure.
Well, one of the things is that they, I believe